All right, so standard announcements. Muddy's Point Sunday. There's two concept checks in Unit A or Unit 3, 3A and 3B. They're just sort of one of them's due this Sunday, the other one's due a week after that. Mini Project 2, which is up through immunocomputing, is due on Sunday, and then a Mini Project 3 from this unit is due a week from then. So that's the kind of schedule. The last time we started in on multi-criteria decision making, of which a subset. So we've got multi-criteria decision making, and that in itself is a subset of, or is a superset, I guess. So a subset of that is multi-objective optimization, which is sort of our main subject here, and a particular subset of multi-objective optimization is game theory, and we use that as our motivation. And that motivation there was that whereas before we had a single objective, now if you consider multiple agents running around, then you might have each one of them might have a different objective, but each one of their actions affects the attainment of objectives by the others. So you can have these kind of multiple objectives, which are the multiple utility functions on each agent. And so that will end up looking like something like this, where you could say I've got agent one, who themselves can take some action, but so can all the other agents in the mix. So I'll say go up to M. And then I've got, all the way down to agent M, who also has the same parameters affecting, but agent one only can affect that parameter, and agent M can only affect that one there. So the idea behind this simple, game here is that, yeah, we want to come up with some sort of solution concept. And so there are different forms of solution concept. And for a lot of games, then a lot of times people prefer the Nash equilibrium, which would just say that at the Nash equilibrium, the way you might phrase it is that there are no unilateral, and that's the key word here, deviations can result in an increase in utility. So if you're at the Nash equilibrium, if everyone's at the Nash equilibrium, if no one else moves but you move, you're going to do worse off. That doesn't mean that you can't do better if others work with you to do better. But this is sort of assumes here, assumes no coordination among agents. And for so-called continuous games, then this is equivalent to saying that the partial derivative of each utility function with respect to the variable that is related to that agent, all of them are equal to each other and equal to 0. So for discrete games where you only have certain discrete actions, this doesn't necessarily hold. But if you're saying, like, I'm trying to choose a temperature that makes me comfortable, and you're trying to choose a temperature that makes you comfortable, and your room, so if I got two rooms in a building, it might be like, this is the you might consider this being temp in room 1, and this here is thermostat in room 1. And then likewise, then this one down here might be the temperature in an adjacent room, and this might be the thermostat in an adjacent room. So you can set that thermostat to any smooth temperature you want. And as it gets hotter in your room, you might make it colder. You might make the thermostat colder. If it's colder in your room, you might make it hotter. But as you're adjusting the heat that's going into your room, there's going to be some parasitic losses to the rooms next to it. So if you heat up your room, it's going to heat up the rooms next to you. And so if you're just trying to make it most comfortable in your room, and they're just trying to make it most comfortable in their room, and you don't ever cooperate, you don't ever go to it next to it and say, hey, I'm about to turn my heat up, can you do this? If you don't ever come up with a strategy, if you're completely disconnected from them, aside from the outcome of your effects, then you would expect this process to come to an equilibrium, which might be described by this expression down here, where at the point where if a Nash equilibrium exists, then it will be at an equilibrium where there will be no benefit, like you will be given the parasitic input from all of the rooms around you, you will be at the best you can be in terms of your utility. And likewise, given the parasitic input from your room and all the rooms around you, then they will be at the best that they can be. And so you'll all be sitting for it. So this is each one of these functions has multiple variables. We're only slicing them along. So this function here, you can view it as kind of a hill that has lots of dimensions. So you can climb up the hill in the x1 dimension, the x2 dimension, and so on. But we're only slicing it in the x1 dimension and then seeing, so it'll be at a plateau in the 1 dimension, but it might be at a saddle or something else in other dimensions. We don't care about that. So it's at a peak in this dimension, and this one's at a peak in this dimension, and so on. And that is sort of a mathematical statement of the Nash. That is what you get, when you've just got these sort of, again, like, uncoordinated equilibrium. So this has applications in, say, multi-agent reinforcement learning, which we'll talk a bit about reinforcement learning in a few weeks. But let me get rid of that. Sorry about that. Yeah. That will go away in just a second. So multi-agent reinforcement learning, so in this case, you've got a bunch of robots or software agents or whatever, they all can adjust their actions and then receive feedback from those to give them feedback on whether that was a good change or not. And so when you have a bunch of these multi-agents running around, if you only give them a reward based on their local actions, and they all receive different rewards, and they have no way to coordinate with each other, then you have this problem that they can lead to finding a Nash, which might be a good thing, but it might be that there is a better solution out there that if they just had coordinated, then they could have found that. So a Nash solution is not necessarily a good solution. If you've heard of the prisoner's dilemma, the all defect solution is the Nash solution, although it's not necessarily the best solution if you could have coordination among the individuals. So sometimes when we're stuck designing algorithms on networks, if this is the only mechanism we have available to us, is you can just seek out your local gradients, then sometimes what we have to do is figure out ways to design the utility functions and how they're perceived on each individual agent so that the Nash is not that bad of a solution. It may not be the best solution, and the difference between the best solution and the Nash is sometimes called the price of anarchy. And all of this is sort of, trailing off into something you'd hear in a different course. But I'm only mentioning this to emphasize that this is not the only solution to multi-objective and even game-theoretic problems, and that sometimes you might want to seek out other solution concepts. And those other solution concepts might require, collaboration between agents and so on and so forth. But this is the first kind of solution concept you often hear about when we think about these kind of multi-agent sort of perspectives here. So what I want to use that is to motivate then a different solution concept that is often much more useful from a design perspective, because it captures our interests as global designers a little bit better than this. This really captures if you've got agents that are just designed to do best for themselves, then you can get these sort of greedy solutions where the solution just happens to be that no one is actually that happy, and they're all end up kind of getting in each other's way, but they're sort of minimizing the damage of getting in each other's way, and that's not necessarily great from a design perspective. So we would like to sort of elevate to some other type of solution concept, and that's what we're about to introduce. But any questions on this, the Nash? Yeah. Yes. Yes, each of the agents the degrees of freedom. So this might be, so like in this temperature control example, it might be that I have a robot sitting in this room and they have a model of, I say temp in room one, but I could even make this, comfort in room one. And, so this robot sits at that thermostat and maybe it looks out over all the humans in this room and it can sort of use non-contact sensing to measure everybody's temperature and says, okay, everybody looks comfortable. Oh no, you look like you're actually a little warm. You look like you're a little cold. And so the robot goes over here and it says, I am getting a poor utility score from the people in this room. So I am, because it looks like more people are cold than hot, I'm going to up this thermostat. I'm going to make it a little warmer. So that would be sort of the idea here, is that you've got some and this is going to relate to what we're going to call characters in a phenotype, or traits in a phenotype. So you've got sort of different ways. This is sort of the state of the world where robot one controls this, robot two controls this, robot M controls this. Each one of their robots, robot one can measure this, robot two measures this, robot M measures this. So these robots are all coupled physically, but they can't themselves in their decision making do any more than measure the utility that's most local to them. So they have to make decisions based on a local perspective of a utility function, which may be completely different than the utility functions for everyone else. So it really might be that that the happiest this robot's room could be is the saddest this robot's room could be. Yeah. Wonderful question. Does a Nash always exist? And no, it doesn't. So if a Nash exists, this will be the condition. So one of the other things that we have to do, if you are designing systems, so this is what I did in grad school. So if you are designing network systems that have to operate in this sort of way, where you are restricted, where you can only measure something here, even though the effects of other agents are affecting the way things are here. Oftentimes, when you're designing the utility functions or perception of the utility functions, you have to do things to guarantee that a Nash exists. And if you don't do those things, then you can get this numerical instability where this robot goes up and that robot goes down, and so on and so forth. This is actually exactly the same problem if you were to go into an old motel and you're going to a shower and it had sort of a shared manifold for hot water between you and the room next to it. Keep going back to temperature, it's just sort of an accident. But the same thing if you've ever, like, if the person, you both get up in the morning, you both turn your showers on in the morning, they get all the hot water, so then you crank yours up, and then a second later you get all the hot water and it's scalding hot, so you crank yours down. And so there's no guarantee that that thing's going to damp out and you're both going to end up having a steady temperature. But if you if you toy with the way in which the actuator dynamics, the feedback, there's all sorts of things you can do that will sort of help guarantee that you might get oscillations, but they'll be in a decaying envelope. And then there will be an equilibrium. But that's not guaranteed. That you have to specifically design for that. Same thing with these things, is that, yeah, you can't take this for granted. But if it exists, this is how it is described. Yeah. Yeah, local with you have to it's a local maximum with respect to the settings from all the other. So it's almost like U1 has a single degree of freedom, and these are like parameters which just are set by others. So when someone else makes a movement, it changes my utility function. So it's like if the next room over cranks their temperature up, it might completely change the shape of my utility function. If they leave their temperature set high and they just leave it there, then at least I know what my utility function is. Then it's a local maximum, my utility function. But if they then change their temperature, that it may not be a local maximum anymore. It changes the shape of my utility function. So I then need to change. So I'm trying to find my local utility function, but my utility function shape, it gets deformed by the actions of everybody else. That's right. Yeah. So it's this dynamic equilibrium here where as everyone else changes, it changes the shape of the hills that it's like I'm on a train track and I can only move this way and this way on my train track, but the hills underneath my train track keep moving. And so I was here, I'm like, finally, I'm at the top of my hill. And then somebody else over there changes and it causes me to dip. And now the top of the hill's over there. So I'm like, now that they've changed, I have to go, now I'm on the top of my hill. And then, but now that I've moved, then now I've caused their hill to deform. So then they move to try to track it, which causes me to move. And then it keeps going back and forth. And hopefully, if under the right conditions, then what's going to happen here is we all will be on the top of our hills where each one of the shape of our hills was set by the position of others. But we all finally settle down when we all sort of, I don't want to call it agreement, but when it just happens to get to the point um, where everyone happens to be on the top of a hill. Yeah. Oh no, there's a ton of math behind this, and both continuous games and in discrete games. Well, I don't mean by so there are under certain so I mean you don't ever know. Are you asking like do you if you're inside the system, do you? Mhm. Yeah, right. Uh-huh. Oh no, yeah, there is a from if you zoomed out, if you're the designer, if you have all of these functions and you know all of these choices about because effectively when you add those like, actually I'm going to be satisfied if I'm within 5 degrees of the underlying. Well, what you've done is you've developed a new utility function where it's now satisfied within that 5 degrees. So if you have all of these utility functions, then there are deterministic criteria that you can say that yes, because these certain criteria are met, a Nash equilibrium exists. Then there are additional criteria that you put on the numerical process to find it. And if I know a Nash equilibrium exists and the update rule that the robot uses at the thermostat meets another set of criteria, if I have both of those things, then I'm guaranteed that the Nash equilibrium will be stabilized under the control strategy. And so, maybe under and asymptotically, maybe under infinite time, it will reach. So yes, it's sort of a mixture of numerical methods and control theory. And so if you take a good numerical methods course, they might, like a distributed algorithms course, then they might go into those sorts of things. Like I said, there are stuff that I did in grad school. Haven't done a lot since, just due to the contingencies of students that have been in my lab. But somebody like Dimitri Borsikas, who's now faculty here at ASU, used to be faculty at MIT. This was like his bread and butter. So there are quite a few people that could tell you a lot about this. There are old books written about those conditions and how to make this work. So it's a very rich literature, goes back to the late 70s or so. So yeah. All right, so that's the Nash. It was just an intro. Now we want to go to something that I think is more practical. I think arguably a little bit more interesting. I will say that I guess I'll just make a little note here that this is also a related topic, are so-called variational inequalities, um, which is a broader span of problems of which the Nash problem is a subset. And so generally most solutions to the Nash come out of this field of VI, variational inequalities. So, but that's not something that I'm going to test you on or anything like that. Just mentioning another term that if you're interested in Nash stuff and this distributed stuff, then if you do look up those books that I was talking about and like, distributed numerical methods, then you'll start seeing that kind of the calculus behind it all is often calculus that comes from the field of variational inequalities. All right, but there are other ways we can think about multi-objective problems. So for example, the so-called knapsack problem. Where if I start, looking ahead to the genetic ways to solve these things, then we could imagine that I've got a genotype, which is the number, or it's the set of items in my knapsack. And then I have two characters, which are going to be the weight of the sack, but then also going to be the profit from items in the sack. So the idea here is I've got this knapsack of items maybe that I'm going to sell. Maybe it's guaranteed that I'm going to sell them all, but I can only carry so many. So I have these two characters, and so you could say each one of the values of this. So this is a trait, and this is a trait. And these two together are my phenotype. And so the idea here is that now we've got this interesting case where there are two different ways to evaluate the items that I've chosen to put into my knapsack. And I can, in order for me to get maximal profit, which is good, I might also have to carry a lot of weight, which is bad. In order for me to reduce the weight on my back, which is good, I might have to then take a cut in the profit that's available to me. So both of these things have value to me, and I need to figure out sort of a balance between the two of them, thus the multi-objective. So so if I were to draw that out, then you might imagine that this x-axis, I'm just going to say this is the number of the items in the set. So this is the size of the set. And so this may not, there might be multiple ways that I can put 5 items in the sack. So this isn't quite perfect, but it's just a way for me to put it on 2 axes here. And so if this is my total profit, so that would just be the sum for all items in my sack. So that's supposed to be a little lowercase I there, I'll just call it PI. Then for that, then it's generally, as this gets larger, then so does the profit. So generally speaking, we've got a trend that's kind of in this direction. And but it's here, I would like to maximize profit. Put that in a different color. So in order to maximize profit, then it's going to be good for me to move in this direction, which means it's going to be good for me to move in this direction. But my other objective, same axis, the number of items in my knapsack. Here, this is, let's say, total weight, which might just be the sum of all the items in my sack of WI for weight. And that too is going to have the thing that if I get more items, I get more weight. But here it's going to be good to move in this direction. And here it's going to, so thus it'll be good to moving in this direction. So we have potential conflict between objectives. All right, so how do you decide how many items to put in your knapsack? How do you solve this problem? What are some conventional ways that you might think to solve this problem? What was that? The mean of the average of what? Well, so how, but I guess I'm asking is like if I can choose items that give me profit, or I can choose items which reduce the weight on my back, um, then is it, how do I choose the right, how do I balance these two? Yeah. Well, so there are, I mean, so the knapsack problem is a tool used in dynamic, or a model used in dynamic programming, but um, but how do you set up the objective that you use in dynamic programming? So what would be like what, how do you justify that your choice, that the output of that will be the best choice? What does best mean for this problem? Um, yeah, but so what does it mean by balance? So I think, yeah, but how do you find that point? So numerically, like, yeah. So that is one approach. So so this the question of that's brought up is balance. And one way to achieve balance is by weighting. So, let's say option one, we'll try weighting. So we have two objectives. So I could say that I've got my objective one, which is, so I could say that it's a little, I said weighting, but one of my objectives is weight. So I'm going to consider, let's say I've got maybe I'll make this generic. So I've got two objectives, F1 and F2. And let's say I want to maximize both, but there may be conflict. So in this case, F1 might be the weight of the knapsack, F2 might be the negative of the profit of the max. Or maybe I did that backwards. Maybe F1 is the profit of the knapsack, and F2 is the negative of the weight of the knapsack. So by maximizing both, I hopefully maximize profit and minimize weight. So one way to do that is to say, all right, I'm just going to create, and so this is something that we're also going to call scalarization. And I would then create a separate objective, which I'll call maybe F, and it's just going to be some weight times F1 plus, let's say, 1 minus W times F2, where weight is in between 0 and 1. So it's the convex combination of this one and this one. Another way to do that is so-called Chebyshev weighting, or Chebyshev scalarization, is I could say F is equal to a weight times um, let's say the difference. So I'll maybe say F1 minus F1 star squared plus 1 minus W times F2 minus F2 star. And so this here is the best solution with only this objective. And then this here is the best with only F1 objective. And so here, let's say I want to maximize this, I might want to minimize this. So so this is one way to weight up here, where I just sum the two of them together, and I say that I know that it's good to have a bigger F1 and a bigger F2, so I'm just going to weight them and then say I want a big sum of the two. An alternative to that, the so-called Chebyshev version here, is I say, well, if I was doing one on its own, I would know this is the best value of objective one. This is the best value of objective two. So I am going to minimize the distance to each one of those values. And I'm going to weight. So basically, I'm going to penalize. So I'm going to penalize how far I'm away from the best F1 and how far I'm away from the best F2, and then weight the penalties. Okay, fine. But then the question is how to pick W. Because it matters. If you pick W equal to 0, then in that case, you're only going to optimize F2. And if you pick W equal to 1, you're only going to optimize F1. If you pick W somewhere in between, you will, greatly, shift your solution between the two of them. And so it's not trivial. You can't just say, I'm going to add them together, 0.5, 0.5, because you're taking a stance that is entirely subjective. And so that's kind of can be a problem. And the same thing with the Chebyshev. The other problem that will become more obvious as we get more into this is that this solution up here, that is the tempting way to do it, it turns out that there are certain combinations of objective functions that this is impossible to find the right balance between the two of them because they don't have a convex combination. So this will become more clear as we go here. But sometimes there happens to be two different ways that you can mix two different objective functions that have effectively the same weight. And this will only find one of them. And that may not be the best one. So that's the reason why we have this weird Chebyshev scalarization, is that it doesn't have quite those problems, but it still has the problem of how you pick the weight. So, question or question? Yeah, well, I'll go. I think I saw your proto hand first. I'm sorry, I missed the first part of that. You said to find the W. Well, but the W is another parameter. So how do you? I mean, if so, I guess what I've left out here, which I probably shouldn't have, but for shorthand, I left out that each one of these has got an X vector, and that's what you're trying to solve for. So we would like to use gradient descent or ascent to find the best X. And W is a separate parameter which affects that. So if I set W equal to 1, I will find the X star that corresponds to F1. So now if I could somehow set the X, if I could say I want this X to be my best, then I could try to find the W that is most likely to make that X the best. But that's kind of a weird thing. In this case, usually I know my objectives, but I don't know my X. And if I'm using W, I'm blending my objectives in a way in order to try to find the X that's the right balance. Does that answer your question? I think because I left out the X when I was just writing it out, it's not clear that that's the parameter that we're trying to find. So, here, how to pick the W, remember, to find the best, and I'll put best in quotes, X. And there was a question over here too. This second, this is F2. Let me just rewrite, make it a little clearer. This is the one you're talking about. Yeah. So this is just F2 evaluated at X minus F2 star, and that whole thing squared. So that, and then just as above, I'll say note Fi star is optimal value of objective I alone. Okay, yeah, question? So that's an interesting, so that will be something that's going to come up later. So the suggestion was W is a parameter that is subjective. So why don't we solve, we're going to try from W from 0 and then all the way up to W1. So we're just trying every single W in this range. And each one of those W's will correspond to a different X star, a different suggested optimum. And we could just plot all those out. And then we could then ask, our stakeholder, I don't know what weight you had in mind, but for all possible weights, here are the different possible solutions. Use whatever subjective magic you can to pick from that. And that is getting close to actually what we're the type of equilibrium concept we're coming to here. So hold that thought because that will come back. But I do want to mention the warning that if you do that with this one, you end up not finding everything because there is, and again, this will make more sense in a bit here, but the types of solutions that we're looking for, these so-called Pareto equilibria, which we're about to get to, is that the shape of that curve, the shape of that combination of those objective functions can be convex, in which case doing what you just said here will find all of them, but sometimes it's not. And when it's not, this only finds the so-called convex hull of that. And so we'll get to that here in a moment. All right, other questions about, this is just weighting approaches. Now, an alternative, you don't have to do weighting, you could also do so-called satisficing. So another option here, satisficing. And so, and this I think often comes up in dynamic programming as well. So a satisficing solution would be to maximize one objective subject to a constraint on the other. So the idea here is I could rewrite this problem as like maximize objective one subject to the constraint, this is overall values of x, that f2 of x is, and then if I want to, I'm going to make sure I do this in the right direction because now I've got these both as maximums. So subject to the constraint that f2 is at least greater than or equal to some bound. So I'll say this is some w, a case of, maybe it's the case of some, I'll just say a. So this is a minimum bound on f2. All right, so here I'm saying, all right, I really, really care about maximizing my profit. So as long as the weight on my back is less than, I don't know, 30 pounds, then I'm okay with that. If you can get even less than 30 pounds, if you can get 20 pounds, that's great. If that's possible, I want a 20-pound bag on my back that maximize my profit. But if that's not possible, then I will give you up to 30 pounds and then just give me the best profit for 30 pounds. And this is much more like the dynamic programming solution where you don't, you've got, you've got this constraint and there's lots of different things that fit under that constraint. And you're trying to find, of all the things that fit under that constraint, what's the one with maximal profit? That's a fine way to solve this problem too. But again, we have the problem of how to choose A. This is just as bad as how to choose that weight. For me, I might only want 30 pounds. Somebody else here might say, I can take 50 pounds. Somebody else might only want 10 pounds. So for each one of those budgets, those weight budgets, you get very different solutions. So, in fact, when you do this kind of knapsack problem in border security and things like that, there's all sorts of these really interesting cases where you might expect that the things you put in your knapsack kind of grow in a kind of predictable way. Like if you have less than a certain budget, you put these three items, and if you add a little more budget, you add a fourth. You add a little more budget, you add a fifth. But sometimes these problems have they have a qualitative shift where once your budget gets high enough, then you totally change. So for example, if you've got a northern border and a southern border, and the cheap place to deploy your resources is one border, but the most effective place to deploy your resources is the other border, then if you put a budget on your border security, then you will, at low budgets, you'll go to the cheap border. But once you get high enough budgets, then suddenly all your resources go to the other border. So, so that's an example where you can get very different shifts based on what this budget is. So that is a subjective thing. So that's not really that great either. So then you can kind of, I mentioned the kind of Chebyshev weighting idea. You can sort of borrow that, so another option might be to use targets, but your own targets. So this is, again, basically the Chebyshev idea, but it's, this is like Chebyshev. So you could say, All right, I'm going to minimize, for example, the f1 of x minus some f1 target and plus this f2 of x minus the f2 target. And there's, or you could maximize the distance from a target. So I could say I'm going to maximize the distance. So what maybe I want to be far away from these targets, or something, I could even do, I might have different ways I like to set this up. So, different, basically, weighted combinations of penalties based on target distances. And this is sort of inspired by Chebyshev. But again, then the question is how to pick targets. So in order to try to make things objective and easy to solve with a gradient climber, all you've ended up doing is introducing more parameters that now you don't know how to set those parameters. So we haven't really made a whole lot of progress. So inspired kind of by this suggestion earlier about sweeping through these different weights, then the thought is, what about set-based optimization? So this is the biggest problem with how optimization is introduced in like high schools and secondary schools or whatever, is that, and this is the biggest reason why people seem to hate people who suggest they're going to optimize something from them. Because the way we present optimization is that we're going to use a mathematical or computational tool to find the best solution. And so as long as you give me all the right objectives and all the right weights or whatever, then I will tell you this is the perfect design. This is the perfect way to balance things. It's the perfect way to satisfy as many people, and so on and so on and so forth. But you always leave things out. Like, so there's always some objective that is missing. There's some uncertainty in the parameters. So nobody likes that. We're like, oh, well, you're just going to solve for the right choice. I'm just supposed to take your word for it. And that's, was driven. So when we introduce optimization, that's the way we often introduce it, is we are going to develop tools to find the one right way to do it. But in my opinion, this is where we should have started when we introduce optimization in high schools or whatever. When we introduce the public to optimization, this is, I think, where we should start, because this, I think, is a much more realistic way to capture uncertainty and to be as honest about suggestions as possible. And what's beautiful about it is if you can degenerate from multi-objectives to single objective, or if all of your objectives align, this then just naturally collapses to the same old single point optimization that you learned in high school. And so it's a much more general framework. So the idea here is that I've got these two, so imagine two, again, objectives, F1, F2, and I would like to maximize both simultaneously. So what I'm going to do is I am going to, just for kicks, draw them on a common axis where F1 goes up and F2 goes down. So here, this is F1 of X, and this is F2 of X. So it is good to be over here on F1, and then maybe I'll make the F2 a different color. So I'm going to redraw this portion down here in a different color just to make it clearer. I'll make this also a different color. So the x-axis I'll make black. Maybe the negative y-axis I'll make red. And so it's good to be in this direction. And just call this x. So it's a simple scalar value here. Okay, so let's just say that my f1, if I plot it against x, then looks something like this. And let's then say my f2, if I plot it against x, and you remember I'm plotting it going down, so but it's just to put them on the same axis together. So I'll plot it. And it's also hump shaped with the humps in a different spot. Like that. Make Yeah, I think that'll work. Okay. So I would like to rather than focusing on what the best x is, can we all agree on values of x that are clearly bad? And if so, how did you come up with that? So, and maybe, and this is almost going to be a hint here, but I'm going to just to make it easier, I'm going to draw little lines, like maybe from the maximum point here, I'm going to draw a little dashed line from the maximum point here. I'll draw a little dashed line down here as well, just so we can kind of have regions here. Okay, so, and that's a little bit of a hint here. So again, my goal is to maximize both F1 and F2 simultaneously. Rather than focusing on the best way to do that, can we agree on the worst ways to try that? What are clearly bad solutions to that problem? Yeah. Not in between these two dotted lines. So values over here and values over here. How did you come up with that? So the thought is that they probably need to be in between because you probably want to be close to this peak or close to this peak. So there's like a tension that'll be kind of in between there. I like that intuition. This is the answer I'm looking for. Does anyone else have a different way they would like to sort of justify why these areas are bad areas to avoid or good areas to avoid? I don't know, are areas to avoid? Any other thoughts on, so that the solution we heard here was sort of inspired by the intuition that if you want to maximize F1, you're going to be here, F2, you're going to be up here. So it's probably a tension between them, which probably means these are the right solutions. But is there a way that we can more objectively define these as the wrong solutions? What's bad about these? Yeah. Okay. The decent, I like where you're going with this. If I were to suggest this as a solution, could you suggest a direction I should move for a better solution? Would you, if somebody said that, said like, I'm going to choose, let's call this red line that I've drawn here that now I can't let go of. Let's call that x equals 3. If somebody's, and so 0 is over here and infinity is over there. So if this is x equals 3, then would you suggest I should go bigger or lower? Was that a bigger? Why bigger? I agree with you, but why? It'll be better in which objective? Both. Right. It'll be better in both because here, this is getting better, and here, This is getting better. That's what we call a Pareto improvement. When you have multiple objectives, if you are at a point and you've got multiple ways to evaluate that point, if there is a movement direction that improves all of your objectives simultaneously, we call that a Pareto improvement. So any of these points have a Pareto improvement in that direction. Any of these points have a Pareto improvement in that direction. These points have no Pareto improvements. These points in the middle, any movement that increases one objective will decrease at least one other objective. That's why we call them Pareto efficient. They're efficient because they have no improvements. We also call them Pareto optimal. They are where the trade-offs live. Yeah. And I'll write that down, by the way. Go ahead. Yeah, okay. It is, yeah. So I'm going to choose whether to write this down, but we are going to cover basic Pareto efficiency or Pareto optimality, which is it doesn't matter how big the improvement is, as long as you get an improvement in one, if it causes a decrease in another, then we're calling that as a Pareto optimal solution. Now, there is some of this is also overlaps with what we call social welfare theory. And so I've said this as robot one and robot two, but this could be a slice of the demographic in another slice. This could be one group of people, another group of people, and this could be some decision made by government or some other entity. And so then, what good politicians are supposed to do is they're supposed to, if it can make things better for all possible constituencies, they're supposed to do that, right? Politicians are supposedly supposed to live in this area where you're making trade-offs, where if things get better for one group, they get worse for another. But in some ways, that's better than saying over here, where you're like, why are you over here? You could just make it better for everybody if you at least went to here. Then we could start the interesting discussions. But why are we stuck over here? Now, your question is about it comes to, so there's in social welfare theory, there's something called utilitarianism, Benthamism, where you combine these things in a weighted way, which is much more like what we were talking about in those previous slides. But then the question is, who's the weight? So who do you weight the highest? A way you bring a little of that into Pareto optimality, and this is still a utilitarian framework, but it's without those weights, is there's something called Kaldor-Hicks equilibria, or potential Pareto improvements. And what a potential Pareto improvement is, and again, I'm getting a little farther afield than I was planning on, but since you asked, if I can compensate you for your losses out of my gains, we call that a potential Pareto improvement. And that is a slightly different concept here. So if I step here and it increases my utility function by $50, if it decreases your utility function by $5, then theoretically on the side, I can give you $5 and you're exactly where you used to be. I'm now up $45. So I've now, via side deals, adjusted the utility structure. So that means that there are certain things here which may not be Pareto improvements, but they are potential Pareto improvements because of those side deals. And so it changes. So there's another set of solvers to try to find the so-called potential Pareto improvements. And this was because like when Pareto came up with this idea, it was like a good concept idea, but then people realized like it's really hard to find Pareto improvements and it's really hard to agree on how to move when you're in this region because it's really like there's so many different constituents. How can you find something that's best for everybody? It's like, so it turns out everything is Pareto optimal because there's always somebody to be upset. So they said, okay, we need something that's weaker. And that's when they came up with this Kaldor-Hicks sort of stuff. But We don't worry about that with robots because usually we don't have that many robots that we have to worry about always upsetting one robot. We usually can, this is a useful structure for us in design problems, but in social welfare problems, then this is a little naive. Does that answer your question? Does that make sense? Okay, so let me write down that stuff here. So these here, I'll just highlight maybe. I can figure out where the highlighter is. Okay. So here we say it is a Pareto improvement. Sorry about the squeeze there, to move to left. That's these boxes here. And then here, we call this a Pareto improvement to move right. And then, so then here, we say this is, so the X values, we say are the Pareto efficient sets. And so there are no Pareto improvements. Or we could say all trade-off. Yeah. Oh, well, yeah. Well, go ahead because I haven't heard from you as much. Well, what we want to actually come out of this is so by set based is this here, which maybe I'll highlight in blue. This whole thing is what we're going to have as the output. So this is our output. This whole region, that whole X, we are going to design meta-heuristics which produce not one point, but a sample of all these points. So our stakeholder, rather than telling our stakeholder, we're going to find you the optimal design, we're going to ask the stakeholder, what's important to you? And they'll say speed's important to you. Okay, speed, right. What else is important to you? Temperature. Okay, temperature. Okay. What else is important to you? And you list all the things that are important to the stakeholder. And rather than saying, okay, now how much more important is speed than temperature than whatever, we'll just say, thanks. Those are all the things that are important to you. We're going to put those into an optimization meta heuristic, like the genetic algorithm. Now, when you did the genetic algorithm in Mini Project 1, you got a bunch of points, but really you only cared about one of them, like the best point that was close to the top. But you got all this other information and these other points. The beauty of these population-based evolutionary algorithms, which are very popular for multi-objective, is that they output a population of values, where now we'll use the whole population. So we'll be able to give our stakeholder, we'll say, none of these things are bad choices. This is the trade-off. You said you like speed, you said you like temperature. So there are designs which run cool, but happen to be slower. There are designs which run hot, but happen to be faster. I don't know what's better for you, but now that I've plotted out, and that's what I'm going to show you next, we plot these objectives next to each other, there might be a strong trade-off or a weak trade-off. Our stakeholder might not know how strong the trade-off is, but we might see that actually there's not much of a trade-off here. So if you actually give up on temperature, you can have it to be as fast as you want, because if we were just to blindly minimizing temperature, we actually don't end up paying that much of a cost in speed. Or we don't, sorry, pay much of a cost in temperature. So you may as well just have the highest speed. Like it may be once we plot the trade-off, if there's not a strong trade-off, they'll be okay with reducing it to, or we can just boil this down to one objective. Or if we do show them it's a strong trade-off, then they'll say, wow, I actually don't know what's best. I need to go back to my stakeholders and figure out what best to use in this design. So it allows for much more conversation between you, the numerical optimization expert, and your stakeholder, who's a domain expert in marketing, and their stakeholders, who are the customers trying to actually put the product out. So that's the beauty about Pareto optimization over standard optimization that you learn about in high school, is it starts conversations, it doesn't end them. So it is a set-based optimization where we output a set, not a point. Does that make sense? Was there another question earlier? Mm-hmm. Yes, for if you had 15 objectives, a Pareto improvement would all 15 increase. At the instant that you move in a direction that one of those 15 goes in another way, that is that you've just found the edge of the trade-off space, and that is a Pareto optimal solution. Yeah, right. So it'll be easier here, maybe on the next slide, where I'll plot F1 against F2, but um, but basically there are these Pareto efficient, or well, as we'll see, the Pareto optimal manifolds um, where the dimensionality. So right now we have two optimization objectives, and so we end up having 1 degree of freedom in our Pareto efficient set. If we had three optimization objectives, then we would have a planar Pareto efficient set. So we now have 2 degrees of freedom in our Pareto efficient set. So the Pareto optimality ends up compressing things to a manifold, which is going to be one less dimension than all of your objectives combined. So it still leaves significant flexibility. It just kind of squeezes out all the bad solutions. So these are definitely, I'll just write this here. This are definitely bad solutions. And then these here are reasonable solutions. I don't want to call them good, they're just reasonable. So what I mean by reasonable is that if you were to pick a solution here, you might have to defend your trade-off, but nobody uniformly, there wouldn't be a bunch of people saying that, oh, that was stupid. They would just be like, oh, okay, that you balanced things this way, and that's why you chose that solution. If you chose a solution here, then people say, why the heck did you do that? If you would have just moved a little bit over, it would have been better. So uniformly, everyone can agree that you should never design something here. You should never design something here. Here you can argue about how to balance things, that's a reasonable argument. It's sort of unreasonable. There's just no way to argue why you might put something in this space of the design space. All right, so that's the basic gist behind Pareto efficiency. So I'd like to plot here, before we close, the kind of normally when we plot these things, you don't plot that the Pareto efficient set. You can, but you often don't. Instead, you plot the Pareto optimal or Pareto frontier. So I'm going to plot effectively a parametric plot here, where I've got F1 and F2 up here. X could be a gazillion dimensions, but I'm only plotting the optimization objectives. And so this will give me a space here of points. So maybe it's got this upper ridge down here. And so there can be this whole area down here. Yeah, that's fine. This whole area down here are all of the feasible combinations of F1 and F2 for some value. They're always so surprised. I mean, maybe it's, I mean, the permutations, like maybe it's a different person every time. It's got to be, but anyways. So they're all feasible combinations of F1 and F2 for some value of X. So you can choose some X that lands you in this region. But from each one of these regions, the Pareto, if we're trying to maximize both F1 and F2, then the Pareto improvement direction is in this direction here. And so this space up here is the so-called Pareto frontier. And so the Pareto-efficient set are the set of decision variables that live in the Pareto frontier. The Pareto frontier are the set of optimization objectives. And so this sort of shows that we want to initialize our heuristic here and then have it move up. And then that optimization meta-heuristic will then sample from this. And so then this will hopefully then be a, our meta-heuristic produces a community of solutions that capture different trade-offs, choices. And that's what we mean by Pareto optimal, the Pareto optimality. All right. Any quick questions? Well, actually, I just let you guys go. If you have any questions, feel free to come up after, and we'll pick up from there on figuring out how to actually solve for these things using these population-based algorithms.